Thank you very much for the invitation. And now I would like to switch to Northern Hemisphere, because we know that the Northern Hemisphere, in Northern Hemisphere, we had a large glacial interglacial cycle and a large change of ice sheet and sea level, contribution to sea level. It was more than 100 meters sea level change during the last, in 10,000 years at the last termination. So I would like to first start by introducing our new method to try to simulate this ice age cycle, and also would like to try to challenge to explain the quaternary transition, which switched from 40,000 years cycle to 100,000 year cycle. And also, we like to emphasize that it's there are many, although there are many conceptual models, it cannot be compared to many fruitful observations like geographical distribution of ice sheets and many features that is observed. So I would like to use ice sheet model, three-dimensional ice sheet model, which is driven by the information of GCM, to try to test these many hypotheses. And also, I would like to do the show you several sensitivity studies to try to understand what's going on, what kind of feedbacks are important for these glacial interglacial cycle. So as David was showing, this is the last 5 million years information from the Delta 018 from Liziki-Ramo, and it of course contains not only the sea level information but also other information, but it's quite identical to sea level change. So we like to ask ourselves why this system changed from 41 kilo-year cycle to 100 kilo-year cycle. Also, we like to try to understand this ice sheet distribution, that we had a larger Laurentide ice sheet or North American ice sheet, larger than the Eurasian ice sheet. So we will try to see try to simulate the ice sheet and link the different observations on sea level and ice sheet during the ice age cycle, like the amplitude or change rate, termination timing, and geographical distribution, and try to understand why the ice age cycle is now 100,000 year cycle, and also whether it is mainly driven by the orbital parameters, or the role of CO2 is important in glacial interglacial cycle. And also to try to understand this Pleistocene transition. In my approach, I have several. We will do several. We have done several GCM runs coupled to slab ocean. Not yet with a coupled ocean, but it will be the next challenge. But we do several snapshots in advance, because it's not. It's too expensive to run this model throughout many glacial cycles, and estimate the sensitivity of temperature precipitation over ice sheets to the forcings like orbital forcings and CO2. Also, the influence of ice sheet upon atmosphere is examined in advance by the GCN to determine the parameter in the ice sheet model. This is similar to the approach of Dave Pollard, but for Northern Hemisphere, since the geographical distribution is quite complicated, we had to separate a lot of effects that I will explain later. Also, then I'm using this GCM information and examining the response of the three-dimensional ice sheet model of Northern Hemisphere ice sheet to orbital forcing and CO2 forcing for several glacial interglacial cycles. These are a kind of snapshots of the to extract the information of ice sheet influence. For example, by the upper figure A and B, these are with different boundary conditions with a smaller ice sheet and a larger ice sheet. In this case, in advance, I will use reconstructed or modeled ice sheet by ICE 5G, by De Peltier in this case, for 12K A ice and LGM ice. But this is just a kind of example, so the following runs in my ice sheet model will not see the ICE 5G or the Dix shape. Just I use it as an example and how the ice sheet shape could influence the ice sheet. And first case, I'm extracting only the flat ice sheet influence by putting a flat ice sheet without the topography, but taking into account the area distribution of these different ice sheets. And then, as you see, these are showing kind of albedo effect of these flat ice sheets. Larger the ice sheet is, you have the larger cooling. And this is a very important information, and we know this as albedo feedback in general. And now, if I compare an influence experiment with a full topography and a flat ice sheet topography, a flat ice sheet case, then I can extract the topographical effect. And if I assume a lapse rate, of a certain lapse rate, then I can separate the local topographical effect and also then the residual. This is the residual of the whole. You will see that, of course, the higher the ice sheet is, you get a cooler temperature over the ice sheet, of course, because it's proportional to the lapse. The cooling is proportional to the height of the ice sheet by the assumption of lapse rate. But the important thing is the residual has quite a lot of information or the meaning. It's not just a noise, because when there is some theory that the planetary wave of atmosphere is influenced also by the topographical effect of ice sheet, and it's shown by linear models or some simple models. And then if we look at our GCM and the geopotential height, how the pressure patterns are modified, you will see this kind of pattern. And it's quite similar to the temperature residual, which shows that this is not just a noise. As you see, the Northern American ice sheet around North America, you have a warmer Alaska or cooler Labrador part, or you have a cooler Europe and warmer Central Asia with this modification of planetary wave, which is just what explained by this geopotential height and by this theory. So we have these now three major influence, and in my previous papers I was just driving the ice sheet with these two, but today I'm adding this part for the rest of the talk, and I will show that this part is playing quite a big role for determining the size of Eurasian ice sheet. Now I'm driving my ice sheet model, which is a conventional three-dimensional ice sheet model with a shallow Earth approximation, but takes into account the temperature and then interaction between temperature and dynamics, and also the delayed bedrock isostasy, and also the calving or the grounding line flux at the margin of the ice sheets. This is applied for Greenland or Antarctica at present day. And then this, the shape, the modification of shape or altitude and area is given back to here. And this is now driving, this is all the summation of all the information that I was extracting from GCM added to the observed temperature or precipitation field as observed present day taken from era 40 climatology. So I'm adding the experiments information of the orbital forcing or CO2 direct effect, and then this ice sheet, separated ice sheet atmospheric feedback effect according to the size of the ice sheet. So this is the time series of the orbital parameter or the carbon dioxide in the past. I will show you the last 400,000 years in the rest of the talk, and these are the isotope data in this time frame. You'll see the spectral analysis of this of each time series and a conventional 100,000 year cycle dominating the 41 and 2319 in carbon dioxide or delta 18. Now I'm going to show you the results. This is the last ice age cycle for the last 120,000 year cycle, and you will show that already the Laurentide ice sheet is starting to grow a lot, and then retreats very quickly. So this is the time series of this model. I was showing this part in this movie, but now I will show you the whole. I forgot to explain you the red, the difference between the black curve and the red curve is the difference of in the data of dating. I'm using the in the previous work, I was using the CO2 record based on the dating of ED2 time scale, Putti et al., but now taking into account new dating by Kenji Kawamura, my co-author in this work. With this small change of CO2, I'm getting a better time series like here, as you saw, compared to the delta 18, correct timing here, termination here, 4, 3, and 2, 1. Especially here, with the slight change of the dating of the CO2, I get a very close time series to the isotope. So CO2 is playing quite a big role. Also, the spectral, I'm happy with this, but it's important now with modeling we can try to see what's how is the role of each forcing. Of course, the CO2 is not important, but we like to know how important it is or how important the rest of the forcing is, and we like now we apply a constant carbon dioxide forcing, and so the system is just driven by the insolation. And now, of course, the amplitude is a bit smaller, or the difference, the timing is almost the same, but the amplitude at each timing is a bit different from the original one. But still, we see the 100,000 year cycle. Also, the 100,000 year cycle, the ratio of 100,000 year cycle and 41,000 year cycle is a bit now weaker than the original one. So in this case, CO2 is important for the amplification and also strengthening the 100,000 year cycle. And also additionally, we can see the role of the delay of bedrock response by taking out this effect, adjusting the bedrock immediately to the ice sheet height, and then we don't get any more the 100,000 year cycle. So the combination of these effects, the input of the orbital parameter CO2, and this nonlinearity in the system is together making the 100,000 year cycle peak. But still, we like to understand how this cycle came out. Okay. Oh, it's going. So I wanted to show that this is also the result of simulation. But the important thing is now the 100,000 year cycle is appearing when we decrease the CO2 level. And then also it's just a slight decrease of CO2 level, and then we start to get the 100,000 year cycle. And also I want to show you that this is coming from North America. When I separate the North American part and the Eurasian part, the Eurasian part is not having this 100,000 year cycle, even with a lower drop, lower level of CO2, constant CO2 level. So, but North American ice sheet is having a very large 100,000 year cycle in this model. So it seems that the Northern American ice sheet is driving the 100,000 year cycle, but the Eurasian ice sheet doesn't want to have the 100,000 year cycle. So together, it seems that the peak becomes a bit weaker, and peak becomes weaker. But still, we can see that the Northern American ice sheet is contributing to the switch from 41-year cycle to 100,000-year cycle at a certain level, from 240 ppm to 200 ppm around here, which is very consistent to, for example, the talk given by Bärbel Hernisch working on the CO2 level change. Now I can show you that the difference of this North American ice sheet and the Eurasian ice sheet is partly coming from, of course, partly coming from climatology, but also from this stationary wave effect. The first start is not so different. If I impose an idealistic cooling of 3 Kelvin, then it starts together. But the growth of North American ice sheet is slightly faster because of the larger accumulation, and also a cooler summer in the Labrador area, and then this effect starts to suppress the expansion of Eurasian ice sheet. This is the case with this stationary wave effect, and this is the case without the stationary wave feedback effect. So you see the final kind of equilibrium state is quite different from each other. And now we are looking at the transient state. So if we look at the transient state, again, this is the kind of trajectory. You will see the trajectory here for North American ice sheet and here for the Eurasian ice sheet, and it's always trying to follow the insolation and trying to grow up. And after several cycles, it reaches a kind of it reaches close to the equilibrium, and then disintegrates. By the way, this line, the background line, is the steady state, the final state after applying this forcing condition for many years, for 200,000 years. And then this background is quite different from each other. Eurasian ice sheet is again having this kind of steep kind of threshold in a lower forcing range than Gl-Intgl ice sheet, as I showed you in the previous figure, that is coming from the stationary wave feedback effect. Yes. And that's why the final, the LGM state, which is not the steady state, but trying to follow the steady state, the Gl-Intgl ice sheet is much larger than the Eurasian ice sheet, and Gl-Intgl ice sheet terminates the 100,000 year cycle, and the Eurasian ice sheet has to follow it. This is showing this steady state part, and finally I'm trying to put the Greenland ice sheet steady state, which is also worked out by other people, but also by us. And it seems that it's a tiny part here. If we put because the Gl-Intgl ice sheet, or the northern hemisphere ice sheet, is so large, and the Greenland ice sheet is only 7 meters sea level equivalent. But this part I enlarge here, and we are going to try to challenge this projection for future. So it's very important to try to understand this or predict this kind of threshold, and also to try to simulate the transition trajectory for the future. So now I would like to conclude. The 100,000-year cycle termination is a response to the orbital forcing, even if, without glacial, interglacial, or CO2 change. And the long-term CO2 change, site change by 20 ppm, 240 ppm to 220 ppm, for example, is enough to switch the mode from 40 to 100,000-year cycle world. North American ice sheet is responsible for the recent 100,000-year cycle, for the switch, and also for the shift of the threshold of Eurasian ice sheet, and for the further prevention of the growth of Eurasian ice sheet through through the stationary wave feedback effect. Thank you very much.
The bedrock response seems to be crucial to get the 100,000-year cycles. What is the value? Do you use a constant for the bedrock adjustment time? And what is that value? And is that, would your time simulation be sensitive to that value?
Okay.
Have you done sensitivity experiments?
I don't have the slide, but we actually tried to put a viscoelastic model. Also, Lev Tarasov had a similar study. But it's very interesting that a few thousand years time constant is, even if we apply a viscoelastic model, it doesn't change the result. And also, if we do some sensitivity studies, the result is not so dependent on the choice of time constant. So some thousand years. So in this case, it's 5,000 years. But if I choose 3,000 years or 7,000 years, it doesn't make a big difference. It seems that we need an order of magnitude 1,000 years.